Using statistical methods, the financial department of a hospital arrived at this cost function given over here, where C of x is the cost in dollars for handling x cases per month. And our goal is to describe how the graph of this cost function can be obtained from the one of the elementary functions. And then we also need to see if we can sketch the graph of that cost function. So what do we have here? Let's try to just write down that function over here. We can see that the cost function here given as 0.00048 times cube of x minus 500, right? And then plus 60,000, and then the x is actually and defined only between 100 to 1000, right? So this cost function is only defined within this domain, let's say it in that way. So what type of elementary function do you see here that is in bulb? So what were the elementary function? The identity function, square, cube, something like that, right? So if we look into that, we can clearly see we have a cube here. So we can say that the elementary function is actually, we can assume that this is y equal to x cube. So let's say it in that way. So if we assume this is the elementary function, we are aware of its graph, right? One side up, one side down, and so the left side will be down, right side will be up, right? So that type of graph we'll see the graph later on, but this is the elementary function. But from this elementary function, how did we get this cost function? Let's try to see what type of transformation we have used. So what might have been done? So it looks like we have so maybe a couple of things we can do. One way I see here is actually we can actually, what we can do here is 500 is subtracted from x. So if that is the case, we can use this fact here. If we subtract a number which is positive, right, to the independent variable x, and we create a new function, let's say f of x minus c, then the graph of the new function will be shifted c units to the right. So if that is the case, then you can see here, let's say 500 is the number, so we subtract that on the variable x. That means we try to compute the new function, which is f of x minus 500. How do we obtain that? We replace x by x minus 500. When we do that, we clearly see this term, we get it, which is cube of x minus 500. So the graph of that will be shifted then 500 units to the right, right? So from the whatever is the graph of x cube, we shift that 500 units to the right side then. So okay, that's what the new function will be. But here we also see there is a some number which we multiply by that number to this new function. So when we multiply by a number, when we multiply by a number which is less than 1 to the function, then the graph of the new function will be contracted vertically by a factor of that. So if that is the case, on this case, whatever function we obtain, which is cube of x minus 500, right, which is the 500 units, right, shifted to the graph of x cube, right, whatever is that new function, and we also now contract vertically by a factor of that. Right, so that's what we need to do. So we need to first shift x cube 500 units to the right, and we vertically contract by a factor of that. So that address the first term, but we also have 60,000 added to this new function, and we are aware that if we add up the constant number, let's say positive number, to the function, then the graph of new function will be shifted c units to the up. So if that is the case, whatever graph we have obtained by, let's say, the x cube, we shift 500 to the right side, vertically contract by that factor, and then we now shift 60,000 units up. Let's try to see all of these transformation on the graphing calculator to make sure that we are obtaining the right graph. So we say that the elementary function involved here is actually just the function x cube, right, the cubic function. So this is the graph of that, and since we say that the new graph is shifted to the 500 units to the right side. So let's try to see what type of graph we get by shifting this to the 500 units on the right side. So we can do that by subtracting 500 on the variable x and creating a new function which is cube of x minus 500, right? So this is the graph of the graph of the cube of x minus 500. So this graph is over here. we can change the scale if we want, but this is one of the graph we can see over here, right? So this is just we shift that graph 500 units to the right side, whatever is the graph of x cube. Now let's try to vertically stretch this graph by a given factor. So we chose 0 point what was that, 0.00048. so we are contracting these vertically by a factor of that. So 0.00048, right? So that was the, let me see, x minus 500. Okay, so 0.00048. Okay, so we are contracting by vertically contracting by a factor of that. Okay, but we also need to now actually we need to add what 60,000 units, 60,000. So let's try to add that, and this is the graph of the given function. We can see it look like a kind of a straight line, but remember that if you look into the problem, the domain is actually restricted from 100 to 10,000. So why don't we also do that, and then we'll try to see is it really resemble like x cube. We'll do that by change the scaling, but right now let's also fix the domain. So it is less than or equal to 100, is less than or equal to x, is less than or equal to 1000. So that's what we have given. Where is the graph now? Well, it's like restricted between 100 and 1000, right? So 60,000 units up. So we see the graph is somewhere over here. We cannot see that properly, but let me change the scale. So let me say that the x units are just scaled by 100 units. Okay, so and then let me also change here. Let's say we are not concerned about what is happening on the far left side, so I'll just do up to negative 100 over here, and then here let's say we are just concerned about all the way up to only let's say just 1000 or maybe 2000 or whatever 1500 maybe. Okay, that's it. So only that. Oh wow, you can clearly see when I change the scaling here, well, it resembles like a x cube, but you can see that the y values are actually on the y-axis. The scaling is different, so it's something like even what 50,000 kind of scaled. This is amazing. So since we shifted the graph 60,000 unit up, you can see around here this is 50, 60, 70, 89, okay, 60, right? So somewhere over here you can see on the 5, and we shifted the graph 500 units on the right side. So you can see this is like the x cube originally. The x cube originally it was passing through the origin. Since we shifted 500 units up, and then also 60,000 on the right side, and then 60,000 to the up. So that's actually this one, this origin is shifted somewhere over here, right? So that's what the similarity you can see between the cubic function and then this new transform function.